Hello, everyone. Thank you so much for joining. If you could turn your cameras on, that'd be great, just so we can have more of a personal experience. But today, we have Professor Jim Adams from the Arizona State University School of Engineering. He's a President's Professor and the Undergraduate Program Chair for Materials Science and Engineering. Professor Adams has done extensive research in developing computational models of materials and applying those models to the study of properties and materials. He also has done research in the Autism Asperger's Research Program at ASU, specifically on biomedical issues, including nutritional deficiencies, heavy metal toxicity, and bacterial yeast growth, overgrowths in the gut. And today he'll be mostly talking about a few engineering projects he's worked on and a general discussion of examples in material engineering. So with that said, take it away, Professor Adams.
Great, thanks very much. So what I plan to do is give a presentation about 20 to 30 minutes and then take any questions that you may have. So as Devin said, I've been a professor of materials engineering for many years now. And what I'd like to do is just share a presentation with you that we give to a lot of our freshman students. So Devin, can everyone see this?
Yes.
So what I want to do is talk about careers in engineering, and I'll focus a little bit on materials engineering, but try to keep it open. So materials engineers design, develop, manufacture, and test materials for products to improve people's lives. Materials engineers work in almost every industry, including nanotechnology, aerospace, automotive, microelectronics, energy production and storage, healthcare, military. There's high demand for engineers in general, and generally starting salaries are around $80,000 a year for most engineers, and then rising from there. There's high salaries because there's high demand for the sort of products and services that engineers can provide. So there are many different types of engineering, and material science and engineering relates to all of these. Basically, materials engineers, you need to know what material you're going to make your product out of. So it's a core part of almost all engineering, but it certainly relates to chemical engineering, electrical engineering, mechanical engineering, civil, aerospace, chemistry, and physics, because we use the principles of chemistry and physics to develop and design materials and then apply them for engineering. Also relates to biomedical and computers. So I'll try to be a little broad while still focusing on materials. Materials for automotives are used for many different applications. Used to be cars were made out of steel. Steel is cheap. It's very tough, so it protects people during collisions, but it's heavy. And so over the last 20 years, a lot of steel in cars has been replaced by plastics and composites to make them lighter weight. One of the areas I worked on with the Aluminum Company of America was to design new aluminum alloys that would be lighter weight, specifically for the engines. So engines have been primarily made out of cast iron, which is cheap but very heavy. And so the hope was to use aluminum engines, which are much lighter weight, but they wear a lot faster. So we had to figure out coatings for aluminum engines so it could last as long as cast iron engines. Another project I worked on with Ford Motor Company is catalytic converters. Cars produce a lot of air pollution. And the amazing thing about catalytic converters is by the time you have exhaust, basically unburnt fuel, hydrocarbons, carbon monoxide that would suffocate you, and NO that causes heart attacks. These pollutants leave the engine and go through the catalytic converter. By the time they travel just 3 inches, 90% of those pollutants are eliminated and converted to just water, CO2, and nitrogen gas. Very safe things in comparison. And so without cars, without catalytic converters, imagine we'd have 5 to 10 times as much pollution in our air. If you ever travel to Mexico City, where they don't use catalytic converters for the most part, that would be a huge issue. So I worked with engineers at Ford. We've had catalytic converters for cars for many years, but we did not have catalytic converters for trucks, which use diesel engines. So I worked with them on designing new catalytic converters that would work for trucks, so trucks wouldn't pollute. There's recently been more research on fuel cells, which is a much more efficient way than an internal combustion engine. Rather than burning the fuel, we react it. So it's much cleaner. You get 2 to 3 times the mileage. But nowadays, the big push, of course, is for electric vehicles and electric cars. So moving on, another very important area for materials engineering is aerospace. And so everything from helicopters to aircraft to the space shuttle, which we used to fly, to satellites in outer space. So with aerospace, the key focus is on very lightweight materials. For vehicles like the space shuttle, if we want to have astronauts come back into the atmosphere, the outer surface of those shuttles when they come back is going to reach several thousand degrees. Many times the melting point of aluminum, the main structure we use the aircraft out of, so we have to put very special insulating tiles on the space shuttle and other vehicles so they don't burn up and cook the astronauts during re-entry. We've had our students work with Boeing on design projects. One of the problems with aircraft run into is they can be struck by lightning, and you don't want your aircraft to be destroyed when it's struck by lightning. So one of the projects our seniors are doing right now is looking at a better adhesive that's used to bind composites together to make the adhesive more electrically conducting. So when the lightning hits the aircraft, it's spread over the whole surface and doesn't just destroy a particular place. Engineers also work very much on the engines. Even the best engines we can make for aircraft today are only about 25% fuel efficient. So 75% of the fuel we burn is wasted in vibration, heat, noise. And so working to develop materials that can work at a higher temperature will make the engines more fuel efficient. That way plane travel could be cheaper. Putting satellites in outer space, certainly great for telecommunications, but perhaps another way to generate solar power more efficiently. One of the neat projects we had a group of our undergraduates work on. It was a national competition to build a Hyperloop vehicle. So if you've heard of Elon Musk, one of our generation's most brilliant innovators, he designed what he called a Hyperloop, which was a train which would levitate in air, so it would have no friction with the ground, and you'd put it in a tube which you'd suck out most of the air from, so there's no air friction either. So the idea is to replace plane travel with this Hyperloop, which once you give it a push, if you know your basic physics, then if there's no friction with the ground and no friction with the air, you give it one gigantic push, and then it goes 600 miles an hour until you need to stop it. So he's been building tunnels for this in Las Vegas with a new device he developed that can bore tunnels very efficiently. And this might be an alternative to plane travel, use a lot less fuel and could approach those very high speeds. And our students were in a competition where they built one of these vehicles, and it was tested along with 20 other universities in a national competition. It's neat to see that even undergraduates can get involved in some really exciting projects. Another important area is microelectronics. For the past 60 years, computers have been getting faster every year for one very simple reason. They're still almost all based on silicon, but the way we make computers faster is by making them smaller. So by making computer chips smaller and smaller, then there's less distance for electricity, for an electron to travel from one transistor to another. So just by making the transistors smaller and smaller, we can make the computers faster and faster. But now computer chips are designed so small that some of their dimensions are down to 10 atoms thick or so, We can't go much smaller than that. So now the question is, what's faster than electrons? And that's light. And so there's research been going on for a number of years to try to switch from computers that are based on electricity to computers that are based on light, which would be orders of magnitude faster. And that's continuing to be an important area. And also huge developments in monitors, and the hope that soon we'll have 3D monitors available, probably in the next 5 to 10 years. So you can watch holographic images instead of flat 2D screens. Another exciting area is biomaterials. Both the scanners that are used for CAT scans, MRIs, provide huge ability to understand what's going on in the human body and to help someone if they're sick. One of the most common surgeries done, especially for elderly people who break their hip, is to replace their hip. And so with an artificial bone made out of titanium. So if someone breaks their hip or needs a hip replacement, then what you do is you drill out the inside of the bone and drop in this titanium piece, and then also put a titanium ball here with a socket so it can rotate. And the way this titanium binds to bone is really interesting. You put a titanium porous coating on the surface, kind of like a sponge, and that rubs against the bone. When the bone gets abraded, it grows, and the bone grows intimately into this porous coating and forms a permanent bond. The bond grows into that coating, and that allows people to walk again. It's a very successful surgery. Hundreds of thousands of people in the US have that each year, allowing them to walk when otherwise they may never heal. Another important area is energy production. The exciting thing is that although global warming is a huge problem, we have two great solutions for that. Well, several great solutions. Solar energy has become so incredibly cheap. It is cheaper now to build a solar power plant than it is just to pay for the natural gas for a plant for 1 year. So the cost of natural gas for a plant for 1 year is more than the cost to build a solar facility. So the only limitation to solar is only works during the daytime. And so we need to have a way to store that power. One simple approach is to pump water uphill in a hydroelectric dam, but it's not very efficient. Batteries can be made, but batteries are very expensive. So there's a huge amount of research going on to battery production, especially lithium batteries. The problem is we're running out of lithium. It's not a very common element, and there's not that many lithium mines on the planet. So if we try to use massive energy storage, probably can't rely on lithium. We need to develop other battery materials that may not be as good, but would be cheaper. But nuclear power, very safe under certain conditions compared to other sources of power like coal and oil, doesn't contribute to global warming. But increasing this work on wind turbines, offshore wind turbines, and some radical designs there. So again, renewable energy is a great way to fight global warming, is another important area that many engineers can work in. And Devin's father, I know, had a strong interest in fusion energy, and that's still hopeful energy for the future. Could be much, much more powerful than current methods, but still a long ways to go. Telecommunications and cell phones just revolutionized the world. In much of the developed world where people could not afford computers, they now have cell phones that basically act as a computer for them. So many apps that have been created and developed. I've created a couple apps for the work that we do. Just all the materials engineering that goes into cell phones so they can have higher and higher bandwidth, so we can transport more and more signal, watch videos, to get very high quality resolution, to watch talks like we're doing right now. So many new features, and again, so much research is going into the types of materials that we use for our cell phones, for the monitor, for the battery, for the CPU, for the memory. Another important area, exciting area, is superconductors. So superconductors are an amazing material. Once you put an electrical signal into them, they conduct that electrical signal with no loss ever. So if you make a coil and then put a current into it, you have a permanent magnet. This just shows a picture of a little magnet floating above a superconductor. So this lower right picture is a train in Germany, which floats 6 inches above the track using magnetic levitation, so able to go very fast. Japan had one as well. It crashed. They rebuilt it. Engineering is not always perfect. But also these powerful magnets we use for magnetic resonant imaging. We use super powerful magnets for imaging purposes. We also use super powerful magnets for cell phone towers to be able to split the signal from thousands or millions of people into each person's individual signal. So superconductor is an amazing capability. The problem with superconductors is they only work at about minus 200 degrees Celsius. And so they're expensive. But maybe someday we can invent a superconductor that would work at room temperature. That would be amazing. Then we'd have a lot more floating trains, etc. New types of materials called metallic glasses are increasingly used in industry for a wide variety of properties. Most metals are crystalline, and glassy metals are much, much stronger than traditional metals, but they're also very brittle. So there's some specialty uses for those. So it's fun to invent new materials. A special glass that's been created. Normally it's opaque, but if you send a current through the glass, it becomes clear. So that way, with a flick of a switch, you don't need to turn your blinds. You just send a little current and you can see through your window. Or imagine having that for window on a plane. It's kind of a cool application. Nanomaterials. So materials, when we make them at the nano scale with tens to hundreds or thousands of atoms, have very, very different properties. When we make metals very small, they're super strong. Nanoelectronics can become super fast because there's less distance to travel. Nano sensors can be very sensitive. So to detect an explosive, someone's trying to sneak on board a plane through the plane detection, or to detect what's going on in the human body. A nano catalyst to develop new chemicals. Nano drug delivery is really interesting. Right now, for treating cancer, the #1 killer of humans, right now, one of the main treatments is chemotherapy, where you give a poison that you hope kills the cancer before it kills the person. Instead, the idea is you could put the chemotherapy into a little capsule that's magnetic, guide it magnetically to the actual cancer, and once it's there, then release it. So that way you're putting the poison right where the cancer is and causing much less damage to the rest of the person. So materials for healthcare, very, very important. This is just a smattering of some of the different areas. If you go into engineering, you'll generally spend your first 2 years studying math, physics, and chemistry, and sometimes biology if you're interested. In our program, what we like is you take a materials course every semester. I teach the course for a freshman. We try to have a lab course every semester so you get some hands-on work. And then in your junior and senior year, you have some electives. You can specialize in what area you want to. And we also at our university have a design project. So we have teams of 3 to 4 students work in a design project, often with industry. So we had students, several of our students work with Intel on better ways to make some of the computer chips. We've had them work with Boeing, as I mentioned, for their aircraft, for their helicopter blades. We've had them work for Medtronics on pacemakers, have them work with another company on airbag canisters for airbags and for cars. Just a huge variety of engineering projects, and so great options for students. In our university, about half of our undergraduates work on research, and about half work part-time at companies, and some do both. So we're at a major metropolitan area. Phoenix is the 5th largest metropolitan area. So an advantage is we have a lot of industry around us. I used to teach at University of Illinois, Urbana-Champaign. We're surrounded there for 100 miles by cornfields. There's not much industry there. So there are pros and cons to different schools, and just be aware of that if you want to do engineering part-time or co-op work. In materials engineering, because there's so much new science and new developments being done, we're very research intensive. So we have a much higher fraction of our students go on to graduate school, whereas in most engineering programs, it may be more like 20% of students go on to graduate school. In materials, usually about half go on to graduate school and half go directly into industry in a wide variety of industries. The typical types of careers that engineers have: with a bachelor's degree, you usually go into manufacturing, could be a materials selection, could be quality control. Make sure your parts are all in good shape. But also, if you go on for a graduate degree, a master's or PhD, you might go into the research side of things. But you might also work on failure analysis, figuring out why did a plane crash? Why did a part fail? Why did the battery on your computer go bad? If you're good with people management, about 25% of engineers go into technical management. They often get an MBA, a master's in business administration, and that can be helpful if you want to manage people, manage the business. Some people go into technical sales. If Boeing is trying to sell their multi-million-dollar aircraft to American Airlines, they're not going to have an English major make that pitch. They're going to have someone who understands the technical features of the aircraft. So the engineers would be the salesperson usually. If you want to do research and develop new materials, new processing, new applications, that usually requires a PhD. If you want to develop new products, it's usually a master's or a PhD. And another option is consulting. Consultants generally work long hours. They generally travel all around the country, might work with a company for a few months to a year or two. They generally get much higher salaries and usually will get a job offer from the companies they work with. But it's very demanding because it's high hours and travels. A lot of people burn out on consulting after a couple of years, but a great experience. So typical starting salaries might be about $80,000 a year, so about $38 an hour. Our school and many other schools have a 4+1 degree. So you can spend an extra year to earn a master's degree. And so you get extra coursework that if you want to go more into the development side of things, takes 1 year. PhD takes about 5 years, including a master's degree. Then you end with a higher salary and you can go more into research. A special thing to realize is that we have such a shortage of people in this country going into PhD programs because they're lured away by the good salaries for a bachelor's degree. They don't want to wait for a great salary for a PhD. And so we have such a shortage that most universities will provide free tuition to their PhD students and pay them a couple $1,000s a month, enough to live on. So you're actually paid to go into a PhD program. Right now, half the PhD students in this country are foreign because we simply do not have enough domestic students who want to go into a PhD program in engineering. So if you have good grades, you need to have good grades in college, but then you can go on for a PhD. So hopefully that's a great overview for you, and be glad to take any questions you may have.
One question I had is, like if you could elaborate more on superconductors and kind of the use of them in different fields and like how it'll benefit our modern society.
Sure. So superconductors, a few elements, a few metals, when you cool them down to about 5 to 10 Kelvin, become superconducting. We've known that for about 70 years now, but it's extremely expensive. You have to use liquid helium to cool things down to 5 to 10 Kelvin. One of the major uses for them, as I mentioned, is to create a magnet. So you just create a circular strip and you put a current into that circular strip, and then it creates a permanent magnetic field. So it's very cheap to operate, but you have to keep it very, very cold. So for research accelerators, particle accelerators, they will use superconducting magnets. I mentioned they're using them just for show in these magnetic levitating trains, but a very important use of superconductors is for cell phone towers and for magnetic imaging, where we use the magnetic properties. But about 20 years ago, someone made a discovery. They took a ceramic material, which they didn't think, no one had any idea that ceramics could be superconducting. They just happened to do a measurement of it, and at cold temperatures, and to their amazement, they found out it was superconducting, and they won a Nobel Prize for it. And then suddenly, instead of being limited to metal superconductors that are only superconducting at about 5 to 10 Kelvin, immense amount of research, very intense for about 10 years. And the use temperature went from 5 to 10 Kelvin up to about 120 Kelvin. So it's a huge jump. So now we can cool with liquid nitrogen instead of liquid helium. So it's a lot cheaper, but still not very practical for many uses. If we could get them to room temperature, one amazing application of them would be power transmission. So right now, when a utility company produces power and sends it to your home, about 30% of that electrical power is wasted. Heating is because the electricity, as it travels through the wires, heats those wires. If you ever see birds in Chicago in winter, they'll put their feet on the power lines cables because it's warmer. So if we could replace copper wires for carrying electricity with superconductors, we would have zero, absolutely zero power losses. So that would be a jump of 30% in our electrical capability. We wouldn't lose 30% of power sending it from utilities to companies. Also, it means that magnetic imaging could be much cheaper and then could be used much more for healthcare. And then magnetic trains would be much more common. So the L in Chicago would probably be replaced with the magnetic L, and be a lot quieter too. You probably heard the L pretty loud as it goes by, and magnetic trains just levitate. They're quiet. So this is just a few fun examples.
Thank you.
You talked about the versatility of an engineering degree. Could you possibly talk more about how once you get into the career phase, about how there's a lot of overlap and how there's a lot of possibility to switch between different positions as you're going through your engineering career?
Yeah, I think it's best if I share with you a quote from Intel. So Intel, who I think you know makes computer chips, they say they don't hire materials engineers or electrical engineers or computer engineers. They hire engineers, is how they think about it. Because if you're going to make a computer chip like Intel, you need materials engineers to figure out what material to make the chip out of. You need electrical engineers to design the circuits. You need mechanical engineers to design how we're going to extract the heat. Because right now, the big problem with computer chips is they get hot. And so half the cost of a computer chip today is the very fancy heat systems used to extract heat. So we're actually switching, there's plans to switch to using diamond on our computer chips, because diamond, along with being super hard, is also 5 times more conducting than copper. It's the best conductor out there, so it can help conduct heat away. So basically, the point is, for any product, you need a variety of types of engineers working together as a team. And so one thing that we really stress in college is the students to become very comfortable working in team. It's no longer one person like the Wright brothers building an airplane. For almost all engineering projects, it's a team of people working together, and you need a team of many types of engineers. I didn't mention industrial engineers who plan the factory, how to efficiently have people work in an assembly line, how to include robots into that assembly line. So industrial engineers to plan that out. So many, many different types of engineers used for every industry. And it just, a certain subset for one versus the other. Does that help?
Yes, it does.
And a lot of you may be wondering, some universities require you to declare your major before you apply to college. Some don't require that, but many do. And so if you declare your major, we found that still about a quarter of students will change their major, usually as freshmen. So you might think, gee, mechanical engineering is of interest, but then you say, oh, I just took my first materials course. That's so cool. I want to go into materials engineering instead, or vice versa. So don't agonize about trying to figure out what type of engineering to go into. It's because students, the first 2 years, take pretty much the same set of physics, chemistry, and math courses. And then they also will take an intro to engineering design course. Then it's very easy to change majors your first year. You don't want to wait till senior year, but it's easy to change during freshman year. And when you think about the different types of industries out there, let me just jump to that. When you think about the many different types of industries, it used to be people would go and join one company for their career. Nowadays, it's much more common for people to change and work in multiple companies, and you gain more experience that way. But in terms of deciding what type of job you're going to pick, an example I like to give, it's like picking a job as an engineer. It's kind of like walking into an ice cream store and picking a flavor of ice cream. There are many good ice cream flavors. There are many good engineering jobs. It just depends on what your personal interest is. And so we really recommend students, if you want to go directly after you graduate into industry, go and work part-time at some of these companies. And so it really helps to then get jobs in the summer, or part-time during the year if you're at a big school that has, if you're in a town where you have engineering jobs around. But if you think you want to go into research, if you like to know not just that something works, but you want to know why it works, if you want to develop new products or new research, then you're probably better off with a master's or PhD. A good way to know is do research with faculty. And so materials engineering, as I said, is very research intensive. About half of our students will work with us as undergraduates and then go on for a PhD. Whereas in most engineering programs, it may be 10 to 20% of students will go on for a PhD. There's just less research in those fields. Any other questions? These are all great questions. I'm happy to answer any.
Yeah. Oh, sorry, Sarah.
No, you're good. You're good.
Yeah, I was wondering, where do you see like the future of material engineering really going? Like, do you see it skewing more towards maybe an environmental side due to like the potential rising effects of climate change on society?
That's a great question. So the reason I very much enjoyed materials engineering, and I actually started I earned a bachelor's degree in physics, but when I was there, I was working on making diamond chips, diamond coatings, and I enjoyed it. And then I was offered to go join a material science and engineering program. What I like about material science and engineering is you use your basic knowledge of physics and chemistry, but then you apply it to those areas. So some people like to say, what's the difference between a chemist and a chemical engineer? And the typical answer is about $15,000 to $20,000 a year in salary. So chemists have lower salaries than chemical engineers because the chemical engineers are building plants. And the same physics, very few people get careers in physics. Only about, I forget the exact percentage, maybe 20% of physicists actually, when they get a PhD, will get a job in physics. Most will go into finance or other areas. Kind of sad to waste your whole PhD on that. Whereas in materials engineering, that's a huge demand. So you asked me, where is the field going? It's in so many areas, it's exploding. But let's pick one example. You said an energy. So I'm very environmentally friendly. That's why I worked in environmental in catalytic converters for trucks to make them more clean burning. That's why I worked with the Aluminum Company of America to make lightweight aluminum engines for cars. They would require less fuel. And that's why I worked with Xerox on making solar cells. And so designing new types of solar cells that might be much cheaper to make than others. So I think in the whole energy realm, we're going to absolutely use solar. It's so cheap and just continues to get cheaper and cheaper every year. So solar cells, right now, solar cells are only 10% efficient, and roughly. And so there's a lot of room for improvement there. But what we really need is battery technology to be able to store the power, or another type of power that can be used throughout the day. Wind is variable. You might have a windy day, you might not. The nuclear power, we're using all our nuclear reactors in this country using 30-year-old technology. We have much better capability to make nuclear power plants these days, but you've still got to store the fuel somewhere, the waste fuel. So they may not be ideal. Hydroelectric power are actually decreasing because dams block rivers and cause environmental problems. But with CO2, there's a lot of research going on how we can extract CO2 from the air. You could do it by planting trees. That hasn't worked too well so far. A lot of the tree farms that have tried, the trees die. You have to really pick your location very carefully. But there is a lot of research in materials on how to take CO2 out and store it in minerals, or store it deep in the bottom of the ocean, hoping it doesn't bubble back up, or other types of storage. But it's expensive, but it is certainly one good option. But another great option, just to make hydrogen fuel, another exciting area. Just take water, H2O, separate out the hydrogen and oxygen, and use hydrogen as a fuel instead. Then you just burn the hydrogen with oxygen and you produce water. So you can use your solar cells to split water and then use that fuel, hydrogen, during the rest of the day. Unfortunately, it's not very efficient, but it is one of many options, and you could use it for cars. So I hope that gives you some idea.
Yeah, definitely. Thank you.
So I guess adding on to that question, I know you do a lot of work in biomedical, and what I was really interested in was in the toxicity portion. And do you ever see metal toxicity tie in with microplastic toxicity within your industry and research? Because I know there is a lack of microplastic research in the human ingestion.
So I've done a lot of work on metal toxicity. Lead toxicity was a huge problem in this country because of terrible engineering. Engineers caused massive lead toxicity in this country, very stupidly. We've known for 2,000 years, since the Roman times, that lead was poisonous, because when Rome sent slaves into lead mines, they die within 2 years from lead poisoning. So we've known for 2,000 years lead is highly toxic. But engineers stupidly put lead into gasoline to make it burn a little more efficiently. And so up until the 1970s, we were pouring huge amounts of lead into the air. And then we made pipes out of lead. We suspect 2,000 years ago, when the Romans used lead pipes for the wealthy people, that contributed to their sterility and the madness of the ruling classes. And so we know that lead is poisonous, but we still have lead pipes in this country. And then the big problem was lead paint. that engineers foolishly made lead paint. The advantage of lead paint is you just wipe the surface and it wipes clean. The lead comes right off, leaving behind a nice clean surface, and you get lead on you. And so those combinations led to so much lead poisoning in my generation. The average person in my generation lost about 5 IQ points. Some people lost 30, 40 IQ points. It's horrific. And still we have lead poisoning today. But lead is actually a huge success. And now the average level of lead is about 1/5 of what it was in my generation. The average person, your generation, probably only lost 1 to 2 IQ points, probably only doubled your risk for ADHD. So lead is a huge success story because we've removed most lead paint. We've stopped using lead gasoline in most cases, and we've replaced some, but not all, lead pipes. That's a huge success story. But all the other toxic metals are generally worse. We've had from increased industry, we've had increased exposure. So it's very bad. Microplastics is a whole nother area. It's not synergistic toxicity. It affects the body differently, but it's yet another poison that we're only beginning to better understand. We need more research on it, but it's a huge problem. There are parts of the ocean where for hundreds of miles, we have huge plastic waste dumps. You know, the ocean is not a trash can that empties. It's a trash can we've been filling, and more trash is accumulating there. But I actually just yesterday showed my freshman engineers a great example in the city of Baltimore. They built what they call Mr. Trash Monster. And in a river, they put it in a river and it just scoops up all the trash that flows down the river, kind of like a giant water wheel. So it's a great design. It's pulled out millions of pounds of trash from the river. And so we could and should be doing that sort of process in every river. We should not be using our oceans as a dumping ground, because by the way, we eat those fish, and those fish get those microplastics accumulated in them, and then that gets into us as well. So yeah, microplastics are a huge problem. And by the way, we don't have a good way to get rid of them. Whereas I've done studies with people who are metal poisoned, we have chemicals, drugs we can give them to remove those metals pretty safely. Safe in infants as young as 1 year old, but we don't have a way to remove microplastics. So they're just accumulating in you and me every day. Any other questions? So I think that's a great point, you know, to bring up that engineering, it has a dark side and, you know, the right side. So which type of engineer do you want to be? Someone who focuses on, I had a job offer to help build nuclear bombs. I decided, you know, we had enough nuclear bombs to kill 99% of the people on the planet. I didn't need to help build more to kill 99.9% of people on the planet. But some people choose to do that. And instead, I've tried to focus on making the Earth a healthier place for us. So think about, you know, what type of engineering do you want to go into?
Sort of going in a different direction. Since you are a college professor, what sort of traits do you think you've seen successful students have that kind of like lead them to success in the engineering field?
Yeah, so freshman year is the most challenging for students. That's when most students drop out of college if they're going to. Nationally, the rates are pretty grim. Only about half of students who enter college actually graduate from college, okay? So making it through the freshman year is the most important. And the guidelines there are awfully simple. Go to your classes. If you struggle with your homework, every professor will have office hours. They'll have a teaching assistant with office hours. So go and see them for help if you're struggling. If you're struggling in course, drop out of it. But basically, just manage your time well. Keep track of your homework assignments and attend all the classes, and you'll graduate. It's the students who begin partying or just saying or delay or procrastinate. The big challenge is in college, you're on a much more flexible schedule. And so you have to be much more in control of your own schedule and setting aside times. But the other important thing in college is to be very involved in extracurricular activities. You know, when you go to interview for a job, are you going to tell them about the math class you took? Are you going to tell them about your extracurricular project, which was maybe working on a solar race car, or maybe it was head of a fraternity or sorority? It's actually those people skills, those management skills that are just as important as technical skills. So showing you can work as a team. A great quote is that it's your technical skills that will get you hired and your lack of people skills that will get you fired. So one of my most brilliant colleagues just got fired because he was very rude to his staff, and he would shout at them and they would send complaints to HR. And after enough of this, he was fired. He received warnings and he just couldn't control himself. So brilliant person, but lacked the people skills. And so learning to be polite and respectful to people may sound simple, but it's a challenge for some people. And also cheating. Unfortunately, there is more opportunity for cheating these days, and our university has pretty much a zero tolerance policy for that. So unfortunately, when we give homework assignments for out of a textbook, it's very possible to find those solutions online. And students who do that will coast for a bit, but then when it comes to exams, they'll crash and burn. So just making sure you are doing the work yourself and staying up in it is really important. So I hope that sort of answered the question. Any other questions?
Yeah, sorry, coming back to that same idea of like metal toxicity, I'm just really interested in the topic, and I think it's really interesting to think about too, because there's such lack of regulation. Have you seen any work in your industry that focuses on like setting certain
Standards?
like laws, standards in place
Yeah,
to
so I'll
prevent
give you
things
a
like
great example.
asbestos?
Yeah, so an example I follow very closely is mercury poisoning. Half of mercury in that atmosphere comes from volcanic eruptions. Not much we can do about that, but half comes from industry. Mercury is the most neurotoxic element. It destroys brain cells at concentrations 100 or 1,000 times lower than lead or anything else. So it's really, really nasty stuff. We know that 1 in 6 women in the US has such high levels of mercury in their body. Their infants are at increased risk of neurological damage. We know that. We know that the major sources of mercury are from dental fillings, from coal burning power plants, because then they spill a lot of coal has a lot of mercury in it that gets into the air, and then also from eating certain fish. So the fish that's highest on the food chain gets concentrated in toxins, not just mercury, but other toxins too, microplastics as well. And so the FDA warns pregnant women, 1 serving of shark, 1 serving of swordfish during their entire pregnancy significantly increases risk of brain damage to their infant. And so there should be warning labels, and some grocery stores have them, some restaurants have those warning labels, but many don't. The second area is dental fillings. Mercury-based dental fillings are still widely used in the US. They're called silver fillings, but they're only 30% silver, they're 50% mercury. Why does no one call them a mercury filling? Because no one would be stupid enough, you would think, to put a mercury filling in your mouth. So unfortunately, dental fillings are still widely used. The waste material from a dental filling is so toxic that dentist offices cannot put their wastewater into sewers because it contaminates the sewer water with too much mercury. The leftover mercury from a dental filling can only be placed in a toxic waste container or in a person's tooth. Now, if you think how stupid that is to put toxic waste in your mouth, and yet it is still being done. And I think it's just ridiculous. We have lots of research that dental fillings lead to high levels of mercury in the body. It accumulates in the brain and damages the brain, the kidneys, the liver, etc. And then coal burning power plants. 2 years ago, our president at the time, well, I guess it was about 3 years ago, our president at the time, Mr. Trump, decided that mercury really wasn't a bad thing. So he removed any emissions controls for mercury. He made it much easier for plants to spew as much mercury as they want to into the air with no controls. So unfortunately, we've gone backwards in controlling mercury emissions from plants. But I believe the Biden admission has changed that. I have to be careful not to be politics. Those are just facts. So do you want cheap electricity, but to poison people? It's your choice. So it's again, what I would call the dark side of engineering. And there's always trade-offs. Nothing's perfect, but we want to have good trade-offs. Any other questions?
When you were talking about the energy sector, you mentioned the limitation of batteries. What kind of research is currently going on in terms of making new batteries? Is it going in like the direction of more efficient or more cheaper, or
multiple areas, and it depends on the type of batteries. So most car batteries today for internal combustion car use a cheap lead acid battery. Now, I'm not too excited about the use of lead. Remember how dangerous lead is? So we've got to dispose of those batteries very carefully. And I'd really rather not be using lead at all. It's really a major problem. There's so much, even though lead is less toxic than mercury, there's so much more of it. I'd say it's roughly equally dangerous to humans when you take into account how much there is. But for car batteries, the main focus is, there are multiple focuses. We want to have more power so the cars can accelerate faster. So we want to be able to we want to be able to draw power faster so we can accelerate the car faster. We want to have a longer range, so we want to be able to store it longer. We want the batteries to be lightweight because the batteries for electric cars are a pretty substantial amount of the weight. And we want them to last a long time, so not too expensive. It may cost $5,000 or more to replace the set of batteries after a few years. It's a big extra cost. So there's many challenges to battery technology. Elon Musk is leading some of the great design changes there at Tesla. But that's for car batteries. For batteries for a home, we don't care if they're lightweight, so we can use different materials. So that's a big difference there. But we should care more about I forgot to mention with lithium batteries is of course the danger that if you charge them improperly, they can explode and cause fires. And so that's also a danger. We'd rather our batteries not explode or be flammable. So trying to make them very safe as well. So that's the fascinating thing about engineering, is you're not trying to do just one thing, make your battery cheap. You have to balance all those different constraints. And for a given application, your different features are more important. Weight is somewhat important for a car. It's hugely important for a space launch vehicle, where it costs $10,000 for every pound you launch into space. So you're going to use a very, very different type of battery or power system in a space launch vehicle than you would on an aircraft or in a home. But I think those general areas I mentioned are all very important ones. And also, finding a replacement material for lithium, since we're running out of lithium. There's one huge lithium mine in the US, but there are environmental concerns. The people around the mine don't want it to be mined. They're worried about toxic release from minerals. So in order to have electrical vehicles, to have the cars be clean, we have to put up with some mining and some damage to the environment from the mining process itself. So it's a challenge. Any other questions? These are all great questions.
I think we only have time for maybe one or two more questions, but I had one about kind of the ethics of engineering and how to evaluate the pros and cons of certain decisions. Like a previous example you said was making energy more cheaper at the expense of using more mercury.
Right. So I'll give you one very extreme example. So VW recently lost billions of dollars because they decided to lie to the federal government about how efficient their catalytic converters were. So they added a secret computer switch to their engines so that during testing by the federal government, the engine would run in a clean mode. And then during real operation to get better miles per gallon, it would run in the regular dirty mode. So they lost billions of dollars when that was discovered. And I would wish that the people who had been behind it went to jail. Unfortunately, with white collar crime, they often don't. But that was a very sad decision that people would make, to lie to the federal government. And it was a worldwide lie to every government in the world. And just to be able to pollute more than you were allowed to and make the world a dirtier place than you should be. I think that was a real tragedy, and I don't think they were thinking about if they had any children. So sometimes engineers, engineering, it's like making a gun. You can, in the hands of a criminal, it can be a very bad thing. In the hands of a policeman, it can be a wonderful thing. So engineering is a two-edged sword, and how you choose to use your engineering skills. Are you going to make the world a better place, or are you going to do something terrible? It's unfortunately up to human nature to decide that. And our job in engineering, I give a lot of ethics examples in my class, and I try to let people understand what are the implications of their engineering decisions and what impact it can have on society. And so at least all we can do is let people be aware of their impacts, but ultimately it's up to them to decide. Another tragic case in the US is someone who bought a company that was making a rare drug, and they raised the price 100-fold, made huge profits, but they were violating patents and do all sorts of other things. So they went to jail for 10 years for it. So they were caught and actually went to prison. That's very rare. All right, well, thank you all very much for listening. I enjoyed your questions. I hope you feel you learned something, and I encourage you to consider engineering. Materials engineering is one of many fields, and ASU is one of many great universities to consider, but all depends on what you like.
Yeah, thank you so much, Professor Adams, for taking the time out of your day to speak for us, and thank you everyone else for attending this meeting.
Take care.
Thank you so
Thank you.
much. I
Thank
hope you have
you.
a wonderful evening.